Hi, from this lecture we'll be discussing about governing equations in differential form. Okay, so in the previous chapters we derived integral formulations of the conservation equations of fluid motion, but integral equations are very useful to get overall information about the fluid flow. Okay, so let us say that for example, if we want to consider flow over the bullet as we have shown here. Okay, so if we are considering this problem using integral formulation, what we do is we make a model of a bullet, fix it in a wind tunnel that we discussed in the previous chapter, and make measurements of velocity and pressure field on the boundary of the control surfaces as we have shown here. Okay, so we measure the velocity and pressure field on the control surfaces of the control volume that we are considering for the analysis. So from this we can get global information like drag force or lift acting on the bullet. Okay, so integral formulation will provide global information. Okay, so by global information, for example, we are talking about drag or lift or these global quantities. Okay, however, so let us say that you have designed the contour of the bullet to experience let us say 5000 Newton drag force. Okay, and then you make the model, you conduct experiment, and you compute the drag. Instead of 5000 Newton that you have designed, you are getting, for example, 10,000 Newton. Okay, so control volume analysis or integral formulation only give the value of drag coefficient. It does not give any clue about why we are getting a larger drag. Okay, so we get only global information. It does not provide detailed flow field information. Okay, I hope you understand what I'm saying. So I'm just repeating. You have designed a bullet to experience, for example, 5000 Newton, but you designed it, you fabricated it, but you see that the bullet has experienced 10,000 Newton. Okay, what you get from integral formulation is just these numbers without having any details about why such a drag increase is happening. Okay, because detailed flow field information is not available from integral formulation, or in other words, control volume is treated as a black box. Okay, we take the control volume for the analysis. We measure quantities on the control surfaces. What is happening inside the control volume, this information is not available to us because control volume is treated as a black box here. Okay, so one way of getting more information about the flow field information is to, for example, we take a control volume. Okay, we break it into 4 control volumes, and then each of these control volume we split into another 4. Okay, and we can go on doing this until we get millions of trillions of smaller control volume within the given larger one shown here. Okay, it is possible to break down this larger control volume around the bullet into, let us say, billions of control volume, and that will give us more information about what is happening within each small control volume, and this will give us a better picture of what is happening to the flow field. But is this practically possible? Okay, breaking it into so many number of control volumes, is it practically possible? Yeah. Yeah, surprisingly the answer is yes. Okay, so if you divide the control volume into infinite number of smaller ones, okay, what happens is that control volume shrinks to a point okay, and this will give you differential form of governing equations. Okay, so integral form of governing equation is applicable for a finite control volume. Now we are breaking the control volume into infinite number of smaller ones. During this process the control volume shrinks to a point, then we get differential form. By doing this process we will get differential form from the integral form. Okay, is that clear? Okay, so now the advantage of the differential formulation is that okay, so while the integral formulations are applicable over a finite sized control volume, so differential form is applicable at every point in the domain. Okay, by every point in the domain, what we are saying is that when you do experiments, instead of measuring only the quantities at the control surface boundary at the control surfaces, we measure velocity and pressure field at each and every point in the domain. Okay, how we are going to measure is actually beyond the scope of this discussion. So assume that we have a method to measure velocity and pressure at every point in the considered volume. Okay, so this will give you a complete flow field information. Okay, while integral formulation gives only global quantities, differential formulation can give complete flow field information. By complete flow field information, for example, I am talking about it can be like streamlines. Okay, how the flow behaves when it moves around the body. Then for example, flow separation, which we are going to talk about in the next chapters, what else, etc. So we will get all the information. So streamlines may look like this. Okay, okay, and there can be a flow separation here forming vortices. Okay, so streamlines, flow separation, vortices, all this information we can get by solving the governing equations in differential form. Okay, so while if you consider the scenario that we talked about, instead of 5000 Newton as you expected the drag force to be, integral formulation will give only the value of 10,000 instead of 5,000. But if you solve governing equations in differential form, you will be able to answer why the drag force is larger than expected. Okay, because it provides complete flow field information. Okay, so until now we are just talking about the advantage of differential formulation without actually deriving the equations. Okay, so in this chapter In this chapter we are going to derive in differential form so conservation of mass or mass conservation equation. This is also called as continuity equation and conservation of momentum. Okay, so usually conservation of energy is dealt in an advanced course on compressible compressible flows, but since we are in an introductory fluid mechanics course, we leave out energy equation in this chapter. Okay, and these two combined, they form the most important equations in fluid mechanics. Okay, they call, so together they are called Navier-Stokes equations. Okay, so we are going to talk about this in this chapter. Okay, so let us start with the conservation of mass. Okay, so we can derive the differential form from the integral formulation. Okay, so in integral form from Reynolds transport theorem we can write, okay, from Reynolds transport theorem. If you had forgotten about Reynolds transport theorem, go to that chapter and review this. Okay, that is very, very important and you should never forget. So this will give you rho dV over the control volume plus rho u dot n ds. Okay, so this is rate of increase of mass within the control volume. This is net outflux of mass through control surfaces. Okay, so one way of obtaining differential equation is from to start with the integral formulation and apply the divergence theorem of vector calculus. Okay, so if you don't remember it, let me write it very quickly. So you have an integral defined over a domain. Okay, so that says, no, let me write it this way. So on the boundary we have f dot n ds. This is the surface integral, so that would become, and f is a vector quantity, then that will be equal to volume integral of the divergence of the vector quantity over the volume. Okay, so the divergence theorem relates volume integral to surface integral. Okay, so this is the surface, this is surface integral. Okay, this is volume integral. Okay, now we are going to apply this to the second term, which is net outflux of mass through control volume. So we have, let's say this is equation 1. So after applying divergence theorem, we get the first term remains. Okay, rho dV plus, so we have control surface which is equivalent to this one. Now if we apply divergence theorem, it will become control volume. Rho u dot n becomes del dot rho u dV equals to 0. Okay, so now we do some simple modifications. So both are integral over control volume. So we write dou rho by dou t plus del dot rho u dv is 0. Okay, so this equation must hold for any arbitrary control volume. Okay, so the above equation is not applicable to a specific control volume chosen in a specific shape or at a particular location. This is valid for any control volume that we consider in the fluid flow, right? So from this arbitrariness we can remove the integral, and we can say dou rho by dou t plus 0. Okay, so this is the the equation of conservation of mass. This is also called as continuity equation. Okay, thank you.